Hello everyone. In this video we are going to go over Lab 8 on the speed of sound, but first I would like to do a quick review. We've already learned about how when waves overlap they can combine via superposition. In the figure on the left you have two waves traveling on a string. When they are at the two positions shown, they'll combine to form a wave with larger amplitudes. And on the right, they'll combine to form a wave with actually zero amplitude. This is shown in action on the bottom, where you have a blue wave traveling to the right, you have a red wave traveling left, and together they form this black wave that looks like it's standing still and just going up and down. Now, to be clear, in the bottom picture, or the bottom GIF, there's one single string, the black string. The blue and red waves are just guides to help you see how the wave on the black string is formed. We also learned that if you have a pipe that's closed at one end and you play a tone at the open end, that tone will send a sound wave down the pipe. The sound wave will reflect off the back of the pipe. And if the length of the pipe and the frequency of the tone are just right, you can have antinodes formed at the open ends of the pipe. And we also learned that the closed ends of the pipe always form nodes. This was expanded upon a little bit in example 14.10, which hopefully you went over. If you haven't, I would encourage you to go over it before you continue with the lab. So in the previous analysis, on the previous slide, we started with a fixed length of tube, and we determined what frequencies would resonate at the end of the tube. When we did this example, we flipped it up a little bit. We started with a fixed unknown frequency for the tuning fork, and you adjust the length of the tube until you get resonance at the end of the tube. So until you have that antinode at the end of the tube. Then, knowing the length of the tube and the speed of sound and air, you can determine the frequency of the tuning fork. Check out the resonances on the right side of this slide. Notice that in the first resonance, we have Check out the resonances on the right side of this slide. Notice that in the first resonance, you have 1/4 of the full wave. If you were to extend this wave beyond the open end of the tube, it would look like this. So you have a node at the water level, you have an antinode at the open end of the tube. If you continue upward, you would get another node here, another antinode here, and then another node here for the full wavelength. So you have 1/4 of the wavelength inside of the tube. When we go to the second resonance, we have that node at the bottom, and we have an antinode at the open end, but we also have another antinode and node pair in the middle of the tube. When we go from the first to the second resonance, we increase the length of the tube by 1/2 of a wavelength. The difference between the first and second resonance pictures is this part of the wave right here. And that part of the wave is equal to 1/2 of the wavelength of the wave. So the second resonance tube is 1/2 a wavelength longer. Now note when we go to the third resonance tube, we increase the length again by 1/2 of a wavelength. Right, the difference between the second resonance and third resonance pictures is this part of the wave, and that part of the wave constitutes 1/2 of a wavelength. So every time we go up a resonance, we increase the length of the tube by 1/2 of a wavelength. In today's lab, we're going to flip it up once more. We're going to start with a known frequency for the tuning fork. We're going to adjust the length of the tube until we achieve resonance for the first time. So that'll be shown in the first resonance picture. We're going to record the length of the tube and call it L1. Then we're going to adjust the length of the tube again until we hear resonance for the second time. This is shown in the second picture. We will determine the length of the tube and call it L2. The difference between L1 and L2 is equal to 1/2 of a wavelength, for the exact reason that I explained on the previous slide. In this way, we can determine what the wavelength of the wave inside of the tube is. Once we have the wavelength and we have the frequency, because this is known at the start, we can then determine the speed of sound in air. This slide sort of shows in action what's going to happen in the lab today. First of all, remember that sound waves are longitudinal waves. Here I have pictured transverse waves traveling inside the tube, but remember we have this correspondence between longitudinal waves and transverse waves related to the pressure of the air inside of the tube. So this is easiest to see in the third tube. You have a blue wave that's traveling down the tube. That blue wave reflects off the bottom, the water at the bottom of the tube. When it reflects off the bottom, we represent that reflected wave with the red wave traveling up the tube. Those two waves combine to give you the black wave shown. So if we play a tuning fork at the open end of the tube, it will send a sound down the tube, represented by the blue wave. The sound will reflect, represented by the red wave, and they'll combine to give you the black wave. This is also happening in the first and second resonance pictures. It's just harder to see which direction the red and blue guide waves are traveling. Now at the resonance lengths, the superposition of the sound wave from the tuning fork, which would be the blue wave, and the reflected wave, which is the red wave, at these specific resonance lengths, those two waves produce an antinode at the end of the tube. So the first resonance has an antinode at the end, and the second resonance has an antinode at the end. The antinodes represent points where the amplitude of the combined wave is the largest. When you have a sound with a larger amplitude, the sound will sound louder. So if you adjust the length of the tube so that they're in resonance, so that you have an antinode at the open end of the tube, you should get a louder sound coming out of that tube. And this can actually happen at other points of the combined wave too. For example, in the third picture, the length of the tube is adjusted so that there is a node at the end of the tube. So now you have the red wave and the blue wave combining to produce a black wave that has 0 amplitude at the end of the tube. In a perfect world, this would actually cancel out the sound entirely. So in today's lab, we're going to play a sound at the open end of a tube. We're going to let that sound travel down the tube and reflect up, and we're going to listen for points where the sound is the loudest and where the sound is the quietest. At the points where the sound is the loudest, we're going to record the lengths of the tube, and we're going to use that to determine the wavelength and the velocity of the waves traveling in the tube. Now, unfortunately, today's lab is one of the labs that's really much more impressive to see in person, or hear in person in this case. You'll see a video of it happening, but the video doesn't really capture the audio as well as you would hear it in real life. Luckily for you, I've devised a way for you to do the experiment at home to help fill your time during quarantine. All you need is a plastic bottle with the bottom cut off so that you have an open end at the bottom and an open end at the top. You need a bowl filled with water, and then you need some way to play a tone. I used an online tone generator and I played it through the earpiece in my phone. You're going to hear a tone coming from my phone, travel into the bottle, and then I'm going to raise the bowl of water up to the open end of the bottle on the bottom. This is going to fill the bottom part of the bottle with water, so you'll have a tone traveling into the bottle, reflecting off the water, and traveling back out the open end. As I raise and lower the bowl of water, that's going to adjust the length of the tube where the sound is traveling. As this happens, you're going to hear the tone get louder and quieter. Now, this isn't required, and again, you'll hear the effect happen several times throughout the course of the lab, but in real life, it's much more impressive than it sounds in the video. Okay, here you go. Here's the lab packet for today's lab. The first page explains basically what I explained earlier in the video. I would still recommend you read through it. At the very bottom, it mentions that you should actually add an end correction because the antinode is not formed immediately at the open end of the tube. It's actually a little bit further. And then it says your instructor will let you know whether to apply this correction or not. I am not worried about it, so don't worry about it. The second page shows the math involved. This first equation for lambda, that is what we saw earlier in the video. This equation for the theoretical speed of sound, this is actually an approximation to one of the equations we had in lecture. It was v is equal to 331 times the square root of t over 273. So we'll use this approximation to determine the theoretical speed of sound in air. The experimental speed of sound in air we get from the third equation, and percent error is percent error, of course. The images are very similar to what I had in the slides. These ones, though, are not to scale. And then below that is the data sheet. When you watch the video, you'll see that there's two parts to this experiment. Part 1 is going to be documented on the left side. Part 2 on the right side. Each part had 2 trials. So for part 1, we used a tuning fork that had a frequency of 480 Hertz. The air temperature in the room was 22 degrees Celsius. Then you will record the length of the tube at the first resonance. You'll record the length of the tube at the second resonance. And then you'll repeat this for trial 2. After that, you'll average the lengths from part 1, and you'll use these averages to calculate the difference in the lengths of the tube between the first and the second resonance. After you've calculated the difference in the lengths, you can calculate the wavelength of the wave using the formula at the top. You can then calculate the experimental velocity using the third equation. The theoretical velocity you can get from the second equation, and you use those to calculate the percent error. You'll then do this for the second part of the experiment, where we used a second tuning fork with a frequency of 520 Hz. You don't have to write down any of these numbers. All this information is given in the video. The final page of the lab packet just has some questions that you'll need to answer, and let's check out part of it. The video lays all this out in a pretty good amount of detail, so I will let you watch through that on your own, but I'm just going to skip through it a little bit here just to see what we have. It starts by showing you the setup for the lab. We show you how the lab was conducted right here. Basically, I'm lowering the reservoir on the left side. That's causing the water level in the tube to also decrease. At the top, I'm holding a tuning fork that's sending the sound down the tube. Okay, and then here starts trial 1, measurement L1. You won't be able to hear the sound very well in this secondhand recording of the lab video, so I muted it anyway. But what happens is it's going to start quiet. You'll hear the tone get louder and louder. Right about this point, you'll hear it gets quieter and quieter. So that point was roughly 16.7 centimeters. So I would go back to my lab packet. For trial 1 L1, I would write 0.167 meters. Remember, the number on the tube is in centimeters, but you want to record it in meters. The video then continues with trial 1 L2, trial 2 L1 and L2, and then you'll continue on. Note that our audio setup for the experiment wasn't the best, so you may have to listen very closely and maybe even rewind it and listen a few times to find a good value for those trials. I believe that's all I have to say for this lab video. Good luck.